Hi guys, in the last lecture what we did is we considered the practical transformer in which we removed the assumptions that we made in the ideal transformer. So in the last lecture we considered the effect of winding resistance and we saw winding resistance referred to primary is R1 plus R2 by K square. K is the transformation ratio, and winding resistance referred to secondary is R2 plus R1 into K square. Then we saw the effect of leakage flux and represented it in terms of series reactance, that is called as leakage reactance. Then we constructed the equivalent circuit of the transformer. The exact equivalent circuit looked something like this. This one was R1, X1, R2 dash, X2 dash, R0 and X0. Okay, dash represents we are referring it from secondary to the primary winding. Now, in this lecture, our main objective would be to determine these parameters that we have connected in the equivalent circuit. That is the core loss resistance, magnetizing reactance, winding resistance and the leakage reactance. We need to determine these parameters in order to construct this sort of circuit. So to determine these parameters, we perform some tests on the transformer. Why we test? To determine there are some objective of the test. We need to determine the core losses in the transformer. We need to determine copper losses. We need to determine either R01 or R02 and X01 or X02. We need to determine R0 and X0 in case of transformer. So we need to determine the circuit parameter as well as the core and copper losses of the transformer. So we perform some tests on the transformer. The test that we perform, first one is called as open circuit test and the second one is called as short circuit test. So let us first of all start with our open circuit test. Now in case of open circuit test, what is my main objective? The first objective is to determine the constant losses or core losses in transformer. Either you can say it constant loss or the core loss. Actually in constant loss, dielectric loss is also included in case of transformer, but we usually neglect the dielectric loss, so constant loss become core loss. Next we need to determine the R0 and X0 parameters of the equivalent circuit. So as I told you in testing of the transformer, we have four objectives to determine core loss, copper loss, to determine R0, X0 and the series parameters of the equivalent circuit. So in open circuit test, we are fulfilling our two objectives. One is to find the core losses in case of transformer. Other is to find the parameters of the shunt branch of the equivalent circuit. Now, how will this test be conducted? This test is mostly conducted on low voltage side with HV side open. Okay, we keep the HV side open and conduct this test on the low voltage side. Why? Because this test must be conducted at rated voltage. Whenever we conduct this test is conducted at rated voltage and rated frequency. Now, the rated voltage on low voltage side will be lesser as compared to high voltage side. By definition, low voltage side is a side which has the lower applied voltage or the lower rated voltage. So, if we apply the rated voltage at low voltage side, the voltage applied will be lesser. Suppose the transformer is 230 by 2300 volt. Then this is my low voltage side, this is my high voltage side. If we want to conduct the open circuit test, it is better to conduct on low voltage side because the voltage that we will need to apply is only 230. If we were conducting the open circuit test on the high voltage side, the voltage that we need to apply would be 2300. Okay. So it is much better to apply the rated voltage on the low voltage side because it is easier to apply since it has a lower value. Now let us see what is the circuit connection. Suppose this is my low voltage side, this is my high voltage side. So we connect three instruments. One is the voltmeter to measure the voltage. Since we have to apply the rated voltage, we need to measure it. This is my ammeter. This will measure the no load current. And this is my wattmeter to measure the losses or to measure the power consumed by the transformer. So remember, if ever you want to identify on which side the test is being conducted, wherever side the instruments is being conducted, the parameters will be calculated refer to that side only. So since we have connected all the instruments on the LV side, so the R0 and X0 that we will calculate will be referred to LV side. Remember this. Okay. Wherever the instruments you connect, the parameters that you will obtain will be referred to that side only. They will not be referable or they will not be referred to the other side. For referring them to the other side, you have to take the transformation ratio square. Okay, but by default they will be calculated on the side wherever the instruments are being connected. Let us see the equivalent circuit in case of open circuit test. Here I have referred the entire circuit on the LV side. So this is my R2 dash, this is my X2 dash. But since the circuit was open circuited, here we have kept open circuit. Now, if we approximate the circuit by moving this shunt branch from EMF to the terminal voltage, this circuit would be something like this. This will be R0, X0, this will be R01, X01, and on the other side it is open circuited. Now since the other side is being open circuited, no current will be flowing in this winding. So we can very well neglect this. So this can be drawn something like this. There is no need to consider the series parameters, we can only consider the shunt parameters, since no current is flowing into the series branches. So here what I have neglected is, I have neglected the no load copper losses. As I told you, whenever we draw the approximate equivalent circuit from the exact one, we are neglecting the no load copper losses. So now this is my equivalent circuit under open circuit test. So the current that will be flowing will be no load current I0. The current going here will be IW, current going here would be I mu. Now we have three readings as per the connection. One is the voltmeter reading. Let us say V. Ammeter will read I0, and since we have only shunt parameters, wattmeter will read constant loss. Actual reading of the wattmeter would be, let us call it as W0. It will be core loss. As I told you, dielectric loss also comes under the constant loss, plus no load primary copper loss. The reading recorded by the wattmeter will be sum of these three losses. Now, as I told you, while drawing the equivalent circuit, we were neglecting no load primary copper losses as well as dielectric losses. So we can say W0 is approximately core loss. We are neglecting the other losses. So my first objective is fulfilled. We needed to find the core loss. Then the wattmeter reading will give me the core loss or the iron loss. Now the other objective is to find the R0 and X0, that is the parameters of the shunt branch in case of transformer. Now How to find that? The no load power recorded by the transformer will be, or the wattmeter will be, V I naught cos phi naught. I naught is the no load current, cos phi naught is the no load power factor. So from here I can calculate cos phi naught, because we have wattmeter reading W naught, voltmeter reading V, ammeter reading I naught. Then I can calculate IW, which is I naught cos phi naught. Similarly, we can calculate I mu, which is I naught sin phi naught. This you can observe from the phasor diagram that we draw. This is my flux, this is my I mu, this is my IW, and sum of these currents will give me I naught. This angle is phi naught. So IW is I naught cos phi naught and I mu is I naught sin phi naught. Then R naught is nothing but V by IW, and X naught is nothing but V by I mu. This is the parameters that are placed in the shunt branch of the transformer. So that is how we fulfill our two objectives, to find the core loss in case of transformer and to find the parameters of the shunt branch. Now let us consider a hypothetical case. What would happen if we use voltage is equal to rated voltage but frequency less than rated frequency? Okay, that is I have decreased the frequency but kept the voltage constant. Then V by F would increase, which will lead to increase in Bm, which would lead to increase in phi m, which would lead to increase in magnetizing current. Okay, since voltage is constant, frequency is reduced, V by F will increase, and we know maximum magnetic flux density is directly proportional to V by F. It will increase. So is the flux in the transformer. Flux in the transformer will also increase, which will require more magnetizing current from the source. So first consequence is the magnetizing current increases. Next is, we will see in the next lecture that core loss is composed of hysteresis and eddy current loss. Now hysteresis loss is proportional to frequency raised to the power minus 0.6, whereas eddy current loss is proportional to voltage square. So since voltage is kept constant, eddy current loss will be constant, but frequency is being reduced. Since frequency is being reduced, hysteresis loss will increase. If hysteresis losses increases, what I am saying is hysteresis loss increase and eddy current loss is constant. So what we can say, core losses increase. So magnetizing current increases and core loss also increases. We know that core loss can be written as V into IW. Voltage is constant, so if core loss increase, the core loss component of the current will also increase. So IW and I mu both will increase. Then we know I naught is nothing but under root IW square plus I mu square. Since both IW and I mu are increasing, I naught will also increase. So my no load current increases. If we reduce the frequency, magnetizing current and core loss component of no load current increases. So my no load current also increase. Then that means no load copper loss, which is I naught square into R1, will also increase. We were neglecting the no load copper loss, but now no load copper loss will be increasing. And our no load power factor will reduce because I mu dominates IW. The change in I mu will always be greater than change in IW. So tan phi, which is equal to tan phi naught, which is equal to I mu by IW, will increase. So phi naught will increase and cos phi naught will reduce. That is, if we reduce the frequency, no load power factor of the transformer is reduced. That is, its performance is versely affected. We never want the power factor to be low. Power factor should be as high as possible so that most of the power consumed in the transformer is the real power. Reactive power is considered wasteful, though it is necessary to create the flux in the transformer. But still, it is not usable, it is not useful to the consumer. That is why no load power factor being reduced is a bad thing. Next, let us come on to the short circuit test. Up to now, what we have covered is open circuit test, in which we determine the core losses and the parameters of the shunt branch in case of transformer. So, what are my objectives left? First is to find variable losses, okay. So, in the case of open circuit test, we were determining constant losses. In short circuit test, we determine variable losses. Then we need to find series parameter, that is R01 and X01. So, these two objectives will be covered in case of short circuit test. Now, where do we perform the short circuit test? First thing is, short circuit test is conducted at rated current. Okay. Now, since KVA rating is same on both sides of the transformer, I told you transformer cannot act as amplifier since the power is same on both the sides and it does not use an external power source. Okay. So, it cannot increase the power in the signal. V1 I1 will be equal to V2 I2. Okay. Power will be same on both the sides. Suppose this is LV side, this is HV side. So, since the voltage V1 is less than V2, I1 would be greater than I2. That means current would be higher on the low voltage side and current would be lesser on the high voltage side. Now, since we want to flow the rated current would be higher on the low voltage side and rated current would be lower on the high voltage side. I rated low voltage would be greater than I rated high voltage. Now, since we need to conduct the test at the rated current, it is better to conduct the test on the high voltage side since the rated current requirement is lesser. Okay. So, we will conduct the test wherever the current requirement is lesser. That is why we will conduct this test on the high voltage side and we will short circuit the low voltage side. Again, I am repeating, in open circuit test what we did is we conducted the test on the low voltage side with high voltage side being open circuited. In short circuit test, we are conducting the test on the high voltage side with low voltage side being short circuited. Okay. So, let us see the connection. Here again, here I have placed a variable voltage source. Why we have connected a variable voltage source? We need to flow the rated current. So, what we do is, we will keep varying this voltage and we will record the current. As soon as this ammeter records the rated current, we will take the reading. So, what you have to do is, keep varying the voltage or the input voltage until the ammeter records the rated current. As soon as ammeter records the rated current, we will consider the readings of all the 3 meters. So, here again I will take one reading from the voltmeter, that is the applied voltage, one reading from the ammeter, that will give me the rated current, and one reading from the wattmeter, that will give me the variable losses in case of transformer. So, this will be my high voltage side and low voltage side will be short circuited. So, let us see what happens to the equivalent circuit. The thing is, when rated current is flowing, I told you no load current in transformer is 5 to 8% of full load current. Okay. That means, now since I am conducting the test at the rated current, that means full load current is flowing in the transformer. So, no load current is just the 5 to 8% of the full load current. So I am neglecting any no load current, hence I am removing the shunt branch, because shunt branch consumes the no load current. If we are not considering no load current, then we have to neglect the shunt branch in case of transformer. This will be R2 dash and X2 dash. These are the secondary winding resistance and the secondary leakage reactance referred to the primary winding. Since we have neglected the shunt branch, these both will come in series and the equivalent circuit will be something like this. This will be my R01, this will be my X01. Since we short circuited the secondary side, this will be short circuit, and here we will apply the short circuit voltage VSC. Current will be flowing ISC, which is equal to I rated. As I told you, this test will be conducted at rated current. Okay. If this test is not conducted at rated current in some numerical problem, then you have to map it to the rated current and then only take the values. First convert the current to the rated current. That I will tell you in the problem solving video how to do that. Now let us consider different readings of the meters. Voltmeter would give me VSC, ammeter would give me I rated, and wattmeter would give me short circuit losses or the variable losses. Now since rated current is flowing or the full load current is flowing, the copper losses means the losses that are occurring in the winding resistance will be called as full load copper loss. Full load copper loss because the current flowing is the rated current or the full load current in the transformer. Other case of variable loss is stray load loss. Stray load loss we will consider in the next lecture what is the meant by stray load loss, but stray load loss are also variable loss. And small iron loss. Why is it small? The thing is, when we short circuit the transformer, the voltage required to flow the rated current is pretty less. The thing is, the voltage, short circuit voltage will be around 10 to 15 volt. Since voltage is very much reduced, the iron loss will also be very much reduced. That is why I am writing small iron loss. Okay. Keep this in mind. The voltage required to flow the rated current under the short circuit condition is pretty low. Why? Because VSC is nothing but I rated into Z01. From the circuit, if you see, VSC is I rated into Z01. Z01 is R01 and X01 in series. Z01 is pretty low. It is like 0.5 ohm to 1 ohm. That is why this VSC will be pretty less. Okay. Are you getting my point? The voltage required to flow the rated current under short circuit condition is very low. That is why the iron losses will also be less. So, if we want to map the iron losses, we have to consider that, let us assume that iron losses is proportional to voltage square. So, iron losses under short circuit condition would be iron losses under rated voltage into VSC by V rated square. Okay. Since VSC is very much less than V rated, we will neglect the iron losses under short circuit condition. And stray load losses are almost 0.5% of the full load copper loss. So that will also be neglected. That is why we will consider that the wattmeter reading under short circuit condition gives me full load copper loss. I am neglecting the stray load loss and the iron loss under the short circuit condition. So one of the objectives of the short circuit test is fulfilled, that we needed to find the full load copper loss. Next we need to find the series parameters of the equivalent circuit. To find the series parameter, we will write Z01 would be VSC by ISC and R01 would be WSC by ISC square, because power loss in the resistance would be I square R. We can calculate X01 as under root Z01 square minus R01 square. Okay, that is how we calculate the series branch parameters of the equivalent circuit. But the only problem in the short circuit test is we are able to calculate the equivalent resistance and equivalent reactance, but we cannot calculate the individual resistance and reactance of the primary and secondary windings. We can only calculate the equivalent resistance and reactance. So if we want to find the individual, what we do is we make an assumption that R1 will be equal to R2 dash, which will be equal to R0 1 by 2. Similarly, X1 would be equal to X2 dash, which is equal to X0 1 by 2. We consider both the parameters as half of the equivalent parameters. That is a valid assumption if you want to find the equivalent resistance and reactance. But we can never find the actual values. Why? Because we can only find the equivalent parameters from the short circuit test. Now again, let us make an assumption that current is flowing at rated voltage, but the test is conducted less than rated frequency. We are assuming that the frequency is less than rated frequency. Now if we consider X01, it will be 2 pi f L01 omega L, x is equal to omega L. Since frequency is being reduced, X01 will also reduce. Okay. But R01 is independent of frequency. Actually, the winding resistance is also dependent on frequency to some extent. How is it? If we consider the skin effect, then as frequency is increased, current is restricted to the outer edges of the conductor. Okay, current will be restricted to the outer edges. So, effective area of cross section reduces and resistance increases. Under skin effect, the effective resistance of the conductor increases. So, if we are neglecting the skin effect, we can say resistance is independent of the frequency. Now, Z01 is under root R01 square plus X01 square. Since X01 is reducing, the Z01 will also reduce. Okay. Now, short circuit current is VSC by Z01. I told you voltage is kept constant. Since Z01 is reducing, ISC will increase. Short circuit current will increase. Then full load copper losses would be ISC square into R01. Since ISC is increasing, full load copper losses are also increasing. So by reducing the frequency at a fixed voltage, we can increase the full load copper loss. Then short circuit power factor would be R01 by Z01. Since R01 is constant and Z01 is decreasing, full load power factor or the short circuit power factor increases. Okay. That is the effect of reducing the frequency for the short circuit test. So guys, you must be very well aware how to analyze these sort of problems. That is what will happen if we reduce the voltage or reduce the frequency, because such kind of qualitative question can be asked if not in GATE examination, then in other PSU examination or in the other state board electricity examination. So you must be able to analyze these sort of problems. So let us summarize what we learnt in this lecture. We first saw the open circuit test, through which we determined core loss and we determined the shunt branch parameters R0 and X0. Okay. And we also determined, how did we determine R0 and X0? R0 was V by IW and X0 was V by I mu. Then we considered short circuit test. Short circuit test was being conducted on the HV side because rated current is less on HV side, and open circuit test is conducted on the LV side. It is conducted at rated voltage and short circuit test is conducted at rated current. Here we determine the full load copper loss from the wattmeter reading, and we determine R01 and X01. So this is all what we determine using the open circuit and the short circuit test. So now we can construct the equivalent circuit of the transformer based on the parameters determined from these tests. In the next lecture, we will explain in detail what are the different kind of losses that occur in transformer and how much is each loss contribution to the efficiency of the transformer. That is, which loss will dominate and what will be the value of each and every loss. That we'll consider in the next lecture.